Hello, everybody, and welcome to today's webinar from Technical Toolboxes and C-FER Technologies. So we're going to be looking at probabilistic and defect assessment in pipelines today. I'm Nick Rendell with Technical Toolboxes, and on the line today we have Chance Wright from C-FER and a man that needs no explanation for the Technical Toolboxes crowd, Mr. Joe Pikas. So today's agenda, we're looking at a number of items. We're going to start it off with C-FER. For folks from Technical Toolboxes, maybe it might be new to C-FER, so we kind of want to give them an introduction and a look at the work they've done with pipelines and the work that they're doing today with probabilistic assessments. From there, we'll bring it kind of back to the defect assessment side of the house with Technical Toolboxes, kind of how we go about that, with our own software. And at the end, there will be ample time for live questions with the two of them. On that note, there is a question pane on the right-hand side of the webinar platform you all should see. If you have questions throughout the presentation, please enter them into that Q&A pane, and we'll either answer them live in the moment if they can. If not, we will go through them at the end for as many as we can get to. So with that, I will pass it over to Chance and let him take it away. Thank you.
All right, good afternoon, everyone. I hope you can all hear me okay. Thanks for the introduction, Nick. It's my pleasure to be here today to give this presentation on probabilistic defect assessments in pipelines. So this topic has been one of my focuses during my time at C-FER Technologies, where my other contributions have all been in the area of risk modeling and assessments of pipelines and related facilities. So I have about 20 minutes or so with you here today. So like Nick said, I'll start with a brief introduction to C-FER and our work. I'll give an overview of the different risk assessment techniques and then show how probabilistic assessments fit in this landscape and how they can be beneficial in the pipeline industry. All right, so first up, I'll introduce C-FER Technologies for those that don't know. So we are an independent engineering firm that offers testing, consulting, and software services with our mission of advancing safety, environmental performance, and efficiency in partnership with the energy industry. So we are a not-for-profit organization and a subsidiary of Alberta Innovates, which is an Alberta government provincial corporation which serves as the innovation engine throughout the province. So despite this, C-FER does operate independently of our parent organization. We operate in a self-sustaining fashion with a fee-for-service business model akin to most engineering consultants out there. We got our start as a research consortium in 1984, working out of the University of Alberta. Since then, we've moved into two purpose-built facilities here in Edmonton, which not only house our offices, but also a few large-scale laboratories with some pretty unique testing capabilities. So C-FER gets the opportunity to contribute to a few different industries, but we mostly contribute to the oil and gas industries. And I'll focus on our work with pipelines here. And most of this will fall under the banner of making pipelines safer in line with our mission. So as I just mentioned, we have some unique testing facilities that allow us to perform full-scale tests of pipelines and other systems that are really not possible anywhere else in the world in some cases. So this includes using load frames to push, pull, and bend full-scale pipelines to the point of failure, like you see in the left picture here, where we have a buckled pipeline. We can also mimic the harsh conditions that pipelines will endure in the real world for things such as H2S exposure or high external pressure, in the case of the picture on the right, which was a test of a subsea pipeline that obviously ended with a collapse of that pipeline. So we also do a fair bit of work to evaluate and validate new technologies for use in the energy industry. So in this picture here is our external leak detection research chamber that we use to simulate pipeline leaks. We have various detection technology providers set up their systems simultaneously on a pipeline that's contained within this chamber. And then we simulate pipeline leaks to see which system can detect them and how long it takes for that detection to happen. Besides the physical testing, C-FER also performs specialized engineering consulting work for the pipeline industry. which includes leading work in the realm of quantitative risk assessments, which we'll talk about at length in this webinar. We also have a tendency to lead joint industry projects, which bring together multiple companies to solve an industry problem. And in many cases, CFER will also play a significant role in developing and advancing standards or codes based on all of the testing and consulting work that we do. And finally, the last piece of our pipeline offering comes in the form of engineering software. So we have a few different products at CFER, but obviously the one most relevant here is the Pyramid Risk Assessment software for pipelines, which embodies CFER's 35+ years of R&D work in the realm of quantitative risk modeling for pipelines. So focusing on work we've done in partnership with PHMSA that many of you may be familiar with, I'm sure most of you have heard the potential impact radius model, or the PIR calculation in CFR 192. So CFER was actually mainly responsible for the development of this model, which is of course used to help identify high consequence areas from a natural gas pipeline failure. CFER has also contributed significantly to various risk assessment projects for PHMSA in the past. This includes a critical review of available quantitative models done for the PHMSA Risk Modeling Working Group. We also developed lifetime risk calculations for storage wells, considering potential maintenance activities on those systems. And most recently, CFER is currently contributing to PHMSA's research into composite pipe materials. So our contributions are focused mainly on pipeline integrity and specifically the equipment impact threat. So we've designed and implemented this testing apparatus in the bottom right picture here that mimics equipment strikes on these composite pipes in order to characterize their response and determine the resistance to that type of impact. All right, so with the intros out of the way, we can now get into the focus of this presentation. And I'd like to start us off with a 40,000-foot view of the various risk analysis approaches that are out there. So I'm sure most people are probably familiar with terms like qualitative and quantitative risk, but I think I've found that there's a fair bit of ambiguity around what these terms actually mean and how the different classifications might be useful when building a risk analysis program. So in this slide, I'll give CFER's perspective here of all of these different terms to get on the same page. And these are mostly based on the guidance that CFER helped develop for the upcoming version of the main Canadian pipeline code, CSA Z662. So the first idea here is that risk analysis approaches should be classified at the highest level by the type of risk measured, which is generated by the analysis. So in other words, the output of the risk analysis. And here is where we have, the familiar two approaches. On one side, you have a qualitative camp where you strive to characterize risk using descriptive categories, indexes, or ranges. And on the other side, you have quantitative risk, where you're expressing risk as an expected value of a parameter representing the consequence of failure, something like lives lost or volume spilled. So the first takeaway from this idea of risk measures is that they can only be one of quantitative or qualitative. In other words, the output of a risk assessment is either a specific number with a physical meaning or it isn't. The second idea is that there really shouldn't be any sort of value judgment or an assessment of the rigor involved in an assessment based solely on the label applied to it. Both qualitative and quantitative methods, according to this philosophy, have their strengths and limitations and can certainly exist in parallel. So for example, when talking about the output of the analysis, there is no shame in having a qualitative output if that happens to suit the intended purpose of the assessment better. So I think the reason we have vague terms in the industry like semi-quantitative risk is partly because of confusion between these risk measures, which are the outputs of the risk assessment, with the inputs and the models that are used to produce the outputs, which I'll call the risk method or the risk approach. So traditionally, qualitative assessments are associated and thought to be more subjective, relative, and judgmental, whereas a quantitative risk assessment is held to be more objective, absolute, and involve more sort of analytical models. In reality, I think it's important to realize that all risk assessments are processes which involve multiple pieces of information, and that all of this information will lie somewhere on the scale from completely subjective to objective. So what might typically be framed as a qualitative approach might often be largely based on subject matter expert judgment, but there's no reason why this judgment or even specific parts of the risk method can't be based on objective data and models. Quantitative approaches, on the other hand, might usually seek to maximize objective data and models, but have to use some level of subjective judgment because we can never truly eliminate that kind of judgment in any engineering assessment. So really, the way in which risk is estimated can involve a whole spectrum of types of information that cannot be adequately described by a simple label like qualitative or quantitative. So as convenient as it would be to judge these books by their cover, we do have to do a more rigorous inspection of every risk method before you can make some sort of judgment or value assignment to it. That being said, this obviously hasn't stopped various groups, including C-FER, from trying to pin down more precise labels and categories for the risk methods that are out there. So in ASME B318S, you'll find descriptions of categories like relative assessments and scenario-based approaches, which you may be able to put on this information spectrum in something like this order. Again, the distinction here is between risk measures and risk methods, which allows any of these ASME approaches to feed either into a qualitative assessment or a quantitative assessment. The PHMSA risk modeling working group, which C-FER contributed to, took some issues with these ASME categories, so they produced their own list of categories instead with slightly different names. But again, these aren't definite lines where one category ends and the other begins, as each can involve the whole spectrum of objective and judgmental information. But you will notice that in both of these classification schemes, the most objective category is labeled as a probabilistic assessment. And as C-FER has been a leader in developing and promoting the use of these models within the pipeline industry, I'm going to spend the rest of the time talking about them and their distinct advantages. But again, just like you to remember that these types of methods can be used for a variety of different risk assessment approaches and procedures, and they can be either qualitative or quantitative. All right. So it is widely understood that probabilistic methods provide the greatest opportunity to use objective data and models of all of the risk assessment approaches. In fact, this risk modeling working group went so far as to say that probabilistic models are actually the best practice for all risk-based decision types. So this would be everything from a system-wide assessment of ranked pipeline risk down to a detailed cost-benefit analysis of potential site-specific mitigations, or even, as we'll see in this presentation, assessments of individual defects. But what actually makes a model probabilistic? Well, I'd say there are two important distinctions that make a method probabilistic, and those are, first of all, the consideration of uncertainty in the inputs to the analysis, and secondly, the use of physics-based engineering models to produce outputs. So many of these probabilistic approaches are built on structural reliability theory, which, to review quickly, is of course the idea that you can characterize the load placed on a system such as a pipeline as a probability distribution. And this distribution accounts for uncertainty in the parameters that lead to the load on the system. And you can do the same for the resistance of that system to that specific loading case. In both cases, we are creating these distributions using both the best available data, making assumptions where necessary, and a model which predicts the physical behavior of the system. So with all possible load and resistance combinations known, you can find the proportion of these that lead to a higher load than resistance, which of course is a failure. So you can find the proportion of cases that lead to failure which in other words is an estimate of the probability of failure of that system to that specific load. So let's take a look at what a probabilistic assessment looks like for a single defect, and we'll illustrate this procedure starting with the data that is required for analysis of a corrosion defect as an example. Of course, one of the traditional limitations to probabilistic assessments is the idea that they require a large amount of site-specific data. But in my opinion, I'd say that these days the pipeline industry is really awash with data that wasn't available even a decade ago. So the necessary information for specific probabilistic assessments like this probably already exists, certainly for all piggable segments out there. And there are even many different approaches that will work for non-piggable sections as well that are probabilistic in nature. So the groups of data required for this type of assessment are pipe properties and dimensions, which are things like grade and wall thickness. You also need defect measurements and the associated tool errors, which is important to understand what the true size of the defect might be. Again, these models are based on some sort of physics-based engineering model. So we need to have that model. In the case of corrosion, it's a burst pressure model like modified B31G or RString. And it would be nice also if our model could take into account the error that burst pressure model has in it, because as we know, these models will never be perfect. So we need to account for the fact that the true burst pressure might be different than what the model says it is. And finally, for any time-dependent threat, we need to have some sort of growth analysis that is suitable for a probabilistic assessment. Luckily, these assessments can be pretty flexible. So this growth analysis can take a variety of different forms depending on the best information that's out there. It could be everything from some sort of historical or standard corrosion growth rate to signal matching between inline inspections. With all this information about a single defect, probabilistic methods will often have built-in ways to characterize the uncertainty in that data. For example, uncertainties in pipe properties can typically be assumed based on variation from standards in something like pipe yield strength, which means that no additional data is required over a deterministic assessment to perform a probabilistic defect assessment instead. So with all this information described probabilistically using a combination of assumed variations and given pipeline information, this information is fed into our burst pressure model to produce the distribution of resistance at the location of each defect. The distribution of load in most cases is characterized based on the pipeline operating pressure, either as a maximum value or considering the potential for pressure variations or even overpressure events in a probabilistic fashion. So with this in place, you have your two distributions, you can calculate that area of overlap, and because you're doing this in a time-dependent fashion, you can apply the growth rate and keep track of that failure proportion over time to produce an increasing failure rate for that individual defect. So besides being recognized as best practice, how do these probabilistic defect assessments actually benefit a risk assessment program? So I'll spend the rest of my time going through a few unique advantages to probabilistic defect assessments. So because these assessments center on a physics-based model, they are able to predict the way in which a pipeline failure will occur in much more detail than other methods. So in other words, the relative likelihood of each failure mode can be predicted for each individual defect that you assess. So you will know what the likelihood of a small pipeline or small pinhole leak is versus that of a significant leak versus the probability of a full pipeline rupture. So these different types of events obviously have drastically different outcomes and consequences. So a risk analysis, which keeps track of them all separately, will be inherently more accurate than one that doesn't. Probabilistic methods are also able to achieve more consistency than their counterparts, which rely on higher levels of historical or subjective information. And this consistency is able to be achieved both for the same threat at different locations on a pipeline, as well as between different threats entirely. So to illustrate this, let's imagine that you have a single crack feature, which according to a probabilistic analysis has this red probability of failure curve, which ramps up over time. So this curve reflects the reality of the situation, as we don't know exactly when this defect will fail. We know that it will fail at some point if it is allowed to continue to grow, and so therefore this probability of failure will increase as time goes on. This green line, however, reflects what a deterministic remaining life calculation says about the situation. So this type of assessment is effectively implying that the defect is completely safe up until a certain point at which failure is guaranteed to occur. Now imagine you have a second crack with a slightly different probability of failure curve. Because of differences in this feature or maybe the way it was measured, the probability of failure increases faster over time. But a deterministic assessment would unfortunately be able to, or would miss this sort of nuanced change in how this crack is predicted to increase in failure rate over time. So if you were to set an intervention interval at, say, 50% of the remaining life, you might intervene on this first crack at year 12 and the second crack in year 6. So in this example, if we go and read off the probability of failure level at the time of intervention, we can see that these defects are being repaired at different levels of probability of failure. So in other words, you're intervening at different levels of safety on your system. So while the deterministic method is certainly a way to manage and assess defects, it will inherently lead to some inconsistent safety levels on a pipeline. So probabilistic assessment has the advantage of achieving more consistency between defects of a given threat. You could also take every single one of those defects, perform this probabilistic defect assessment, and then turn those individual points into a failure rate profile along the pipeline. With this in hand, you could layer in the probability of failure from other threats, such as third-party damage, which might not have specific defects per se, but can still be expressed quantitatively along the pipeline. So because you're producing risk in the same units, it is easy to evaluate threats against each other, determine what is driving the risk at each location on the pipeline. And in the case of defect assessments, you can see specifically which defects are driving the probability of failure, which gives you a way to prioritize the repair of any remaining defects in a risk-based fashion that ensures consistent safety levels along the pipeline. And probabilistic defect assessments are also able to take advantage of sort of benefit of most quantitative risk assessment methods, which is that they have the ability to directly estimate the effect or the benefit of each integrity or risk mitigation action that is taken on the system. Because probabilistic models are based on the physics of the actual behavior of the system, they essentially have baked-in sensitivity analysis for any input parameter to the model. So you can imagine if you have a base case risk profile over time, like shown on this chart, you can simulate the effects that a new inline inspection might have simply by removing the defects that inspection tool would likely be able to detect, and then rerunning the calculation to see how that risk changes over time. The burst pressure model that's built into your probabilistic assessment is also able to show you the impact of a permanent pressure reduction on that pipeline to the risk for these defects. And because these quantitative risk measures are threat ambiguous, you can compare these options against something like increased damage prevention, which works to mitigate an entirely different threat. So you can imagine if you have this vertical axis here expressed in physical units like dollars or failures, you get to read the benefit of each mitigation directly off of the chart, quantifying it, which allows you to compare different methods. Obviously allows you to do sort of a cost-benefit analysis too, if you're stuck deciding what the best use of your resources are. And finally, by definition, probabilistic assessments will allow you to quantify the uncertainty within the risk assessment input parameters. So this is beneficial because it allows you to reduce risk simply by getting better data or performing more detailed analysis. So there may be no need for physical changes or actions on the pipeline. I find that this is going to be especially important as the industry faces new challenges and threats, such as widespread hydrogen and carbon dioxide transmission in legacy infrastructure, if that continues to ramp up. To illustrate this, let's imagine you have a pipeline segment, a new pipeline segment to your system, which you would like to characterize the risk of. At first, you might only have historical data to create that risk assessment from. So your estimates of risk will have a lot of uncertainty. In other words, you have a very wide distribution to work with. With a little bit more effort, you might be able to analyze the pipeline with models that look at similar pipelines in the same area and make some sort of comparison and have some sort of algorithm to try to predict the conditions on this segment. So this would reduce the uncertainty, which is represented here by a narrow distribution. Later on, you could perform an inline inspection, taking the vendor specified tool accuracy as the basis for your uncertainty. And then finally, the ultimate goal might be to perform enough verification digs to produce specific estimates of defect sizing accuracy for that ILI run. So this would allow you to get the most accurate and hopefully the least uncertain data on the damage to the pipeline if it exists, so your results have less uncertainty. So you can see as we go from left to right here, and we progress through the different methods that are available, the uncertainty is being reduced, and therefore the probability of failure is as well. So this allows for, first of all, more efficient mitigation and operation of pipelines, but it also allows you to demonstrate the effect of each decision that is made along the way, and you could stop before you get to the final decision if a risk threshold, or the final action if the risk threshold is already met and no further action is necessary. So C-FER did a study on this phenomenon a little bit ago and produced this graph, which shows the large impact that simply more accurate measurements would have on risk estimates. So moving with a tool with an error band of plus or minus 20% of wall thickness to just 5% of wall thickness, the probability of failure in this study reduced by almost 2 orders of magnitude. So this would obviously have a huge impact on the overall risk of the system and would help to provide justification for getting a tool with better accuracy, or perhaps saying that the tool with the given accuracy is already good enough for your risk-based criteria. So that is the end of my part of the presentation. I hope I gave you an idea of what a probabilistic assessment is and how it might be beneficial, at least from a theoretical standpoint. I know we didn't get too far into how we put these methods into practice. So if you're interested in learning more about how these assessments actually work or the tools that perform them, please reach out to me. But for now, I'm going to pass things over to Joe to talk a little bit more about defect assessments in general.
Thank you.
Go ahead, Joe.
Okay. And let me start the slideshow. Could you all see my presentation?
Yep.
Okay, thank you. My name's Joe Pikas, and I'm going to talk about the methodology for defect assessment, where it's tied into probabilistic risk assessment. And I think it's going to be one of the things that Chance and I talked about just you know, regarding the handoff on this is oh, it's running away on me. Are the requirements, and the requirements are going to be basically where does C-FER start and where do they end? And one of the things that we'll be talking about is verification. It's going to be somewhere between the verification and prioritization after an ILI run, and of course, and that's going to be the big handoff between the two systems. Regarding RString, well, RString has been around since 1998, and that's not going away. It's going to be here for a while. It's been proven up. It's been tested, burst tested, and things of this nature. So we know for 20 some years, 25 years, that we've had no issues with the program itself. However, what we're looking at now that we know RString is a solution, how do we manage our pipeline assets while reducing risk? And this is what it's all about. The biggest question I get asked in my RString classes is, hey, Joe, when do I stop doing the verification digs? And I always tell them, when you feel confident enough that that you could sleep at night. Well, that's part of the answer. The other part of the answer is having a program like probabilistic risk. It's going to make you sleep at night. That's going to be the other part. You won't have to take that sleeping pill. And so this is where it's going to come in. So you'll have a criterion or criteria for prioritization, for scheduling, excavating, and of course the assessment of the defects. And this is what it's all about. And then the rest goes without saying. You know, the evaluation of the remaining strength. Like I say, B31G modified and B31G original. I'm going to call those two the BGs. Okay, no relation to the singing group, but you know, they're okay. This is what we've been using for years, but let's be real. They only take 2 readings: maximum length and maximum depth, based on a parabola or modified system, and we'll talk about that. And what about the root causes? What's going on out there? Why are we seeing so much metal loss? Why are we seeing the things we're seeing? Well, we know some of it's mechanical damage, but a good deal is the coatings that we're using. And why are they failing? You know, what types? And I could say just about all types, but some cause more problems than others, particularly when they shield the cathodic protection. And this is the reason why we have isolated pitting and things of this nature. And we need to recognize that. And then we got to go back when we have these kind of problems and reprioritize and classify. And this is where, again, I see the strength coming in, you know, with probabilistic assessments. And then what type of mitigation do we use? And then we'll talk about RString as the solution. Well, it's more than that. So let's talk about from probabilistic to defect assessment. We need to prioritize those ILI anomalies for dig investigations. And as Chance mentioned, he talked about cracking. You know, we're dealing with cracking as in SCC. We got problems in the material itself, the pipe wall, and of course the wells. However, we got to deal now and then with what we call, and cracking usually results in failures, where blunt-like defects usually result in a leaker. So we need to consider these things, you know, as part of the model too. You know, what are we dealing with? Are we dealing with cracking issues, blunt-like, or both? You know, we need to make those determinations. And then they need to determine optimal approach for what type of repairs we're going to be doing. Where does RString come in? Well, it does it's used for the assessment of ILI metal loss. Okay, this is what we're talking about. And it's typically corrosion. It can be a mechanical defect such as gougings, but we need to take the stress risers out and remove them. What about verification and optimizing the inline inspection data? Wouldn't that be nice? You know, the inline inspection guys, they just do their job and say, here it is. It's plus or minus 10%, 80% of the time. Great. Well, how do I verify and optimize this? Now we may have a way to do that. And of course, you're going to have to use engineering critical assessment to limit some of the investigative digs. And then that, of course, will be based on probabilistic assessments too. And then we could determine our reassessment intervals, determine the remaining life, and of course, time to failure type of calculations. Here's the ILI anomaly process. It's been around for years. And of course, we talked about the BGs here and then RString. But what about all these adjustments? This is a problem. How do we get around these guys? And that's always been a big problem. And without some criterion or criteria, we just go out in a field and evaluate in a ditch. This is fine, but we have the missing link in this area here: anomaly and pipeline data analysis. This is where the missing link is in here, and this is what needs to be cleaned up in the industry. And then, of course, we know what we have to do once we find the indications. I'll call them indications. To me, they're an indication until they could be measured and verified. But the way we do it is, again, we determine the failure pressure, and then multiply it by these your safety factor, your design factor, to get a safe operating pressure. And of course, if it's greater than the MAOP, oh, we're good. All we have to do is a recode. However, if it's a no, well, guess what? We either got to lower that pressure immediately, or reduce, or make a repair. So some of this is going to stay the same, but this is the area of concern in here where there's a lot of unknowns. We need to think about managing, and the way we're going to manage, the way I see it, and Chance sees it too, is the verification of defects, and then using the probabilistic risk assessment. And then we could start prioritizing. And like I said, we could schedule, we could do the excavations, and then the assessment of the cracking or non-cracking defects, and then of course metal loss type of defects such as corrosion and mechanical defects. We need to be familiar with the industry standards that we're using and the local regulations, whether you're north of the border or south of or the U.S., the PHMSA, or the Canadian version. So this all works together, and believe it or not, they're very close together. Regarding allowable corrosion, we should be using nominal. Another question that I always asked is, hey Joe, we measured something, the wall thickness a little bit heavier than what was on the as labeled nominal. Well, that may be true, but that doesn't mean it's all the way around the pipe. And I always suggest, if you're going to measure something, you need to measure it 360, and you need to do a 360 investigation, because if you do find metal loss, you could rest assured there may be other type of defects that could be on the pipe itself. And why? Because of coating failures and things of this nature. And why did we have those failures? Either because it was misapplied, or it was misinstalled, where there was damage caused, to the coatings. So please do do a 360 around the pipe. I'm a firm believer, just because you get a dig sheet, you just don't walk out there and just go right to that anomaly or indication. You need to do a full 360 around the pipe. It's a two-step response, viable calculation with the lowest estimated pressure. Basically, you're running a failure or a burst pressure. That's what you calculate first, and from there, it's determined using that max pressure, that's lower than the pressure for safe operations. In other words, you're using that 0.72 design factor or whatever factor you're using. So this is how we get the safe operating pressure. We know about referencing. We know about gridding. We have better tools than this, but these are the basic tools for preparing. We have 3D structured light optical tools. We have 3D laser optical tools for external pitting, and of course, an ABC scan for UT meter for determining metal loss internally and looking for other types of defects, such as laminations and things of that nature. This is the we're going to talk about the original and modified, the BGs here, and what we're talking about is corrosion on weldable pipeline steels. All the calculations are based on that, on weldable pipeline steels. However, some of them, particularly the BGs, are related basically to isolated areas. They were never meant for long length corrosion like RString is. So but they all have one thing in common. They should be smooth contours, and they are, and you'll see in the next slide on the next coming up. Excluded: corrosion in wells or grooves. There's reasons for that. Mechanical damage unless the stress concentrators are removed. And of course, the objective is, to evaluate the structural integrity based on Barlow's formula, which came out in 1890, still used today and around the world. Primary stresses only, and not secondary stresses such as overburden and bending and things of this nature. And here's the problem here with the modified. They're arbitrary. We've got a parabolic shape here and an arbitrary shape here. And the reason that arbitrary shape came out was because this was so conservative. They had to do something because everything was basically a repair. So about the same time this came out as RString. Actually, this came out right before RString. It preceded RString coming out, probably within 6 months of each other. And yet, even when this came out, folks were saying, "Oh, it's too liberal." And when RString came out, they said the same thing. The program is we're not going to use it. I remember when it first came out, and this is one of the things, because it's probably the most accurate one, and it's the most tested one of all. It's been out for over 25 years, and there are no issues with there've been no failures where RString said it wasn't going to fail. So I could tell you where these, if you have a groove-like defect that doesn't represent, let's go back here, the shape, because you're taking the deepest point here, it could actually fail, and yet it would say it was okay, because it's assuming that shape all the time. And that's one of the problems with these with these two is their arbitrary shapes. Specific limitations, coarse mechanical defects, third party, stresses, secondary, which I mentioned, welds, fittings, overburden, combined with other defects, greater than 45 degrees circumferentially, and of course, crack-like defects. And of course, the regulators put an artificial 80% on some of this, which even though it passes the pressure test, you still have to do something. And it was something that the regulators put out, and it's still in effect because you could have a small pit and easily pass the RString calculation, and it will not fail. But but you will have to do a repair regardless. Oh, excuse me. Okay, this is some external corrosion. This is a MIC, microbial induced corrosion, and you could see the hemispherical pits here, steep and deep. They're steep on one side, taper off on the other side. You can see the crack. This is by the way, this is a 30-inch piece of pipe. Here's the weld. If anybody ever wants to see this coupon, it's up at this corrosion school up in Kilgore, Texas. They have a 2-year degree up there. You could get, for students who want to get into that area. And one of the things is you could see this was ready to fail, and this was not caught by a smart pig. This was caught by a close interval survey, and it actually indicated that it was borderline potentials, which we should have never saw. And the guys, I'll never forget, the guys asked, "Should we dig this, Joe?" I said, "Yes." And they said, "Why?" Because your on and off potentials are both the same, and there's something wrong. It's a current drain, or there's something not right here. And sure enough, not only did we find this, but we actually had to replace about 1,000 feet of pipe because of that whole entire area was was related to this MIC that occurred. And one of the things was an older pipe put in the late 40s, and CP wasn't put on the pipe until about 5 years later. So it had a chance to show its mark. Internal MIC is similar, but you could see where here's the girth weld, and you could see how the flow rate, how the flow rates impacted one side versus the other side, the upstream versus the downstream. And the problem is we can't repair this very easily. So what do we do in a situation like this? Well, it's either cut it out or put a type B sleeve on here, a pressurized sleeve, to take care of these areas. However, one thing you need to consider is ongoing corrosion. It's one thing when you're dealing with something like this, if it's fixed, if it's fixable, which it isn't, but something like this, it would probably have to be cut out too. But the point is you have to consider a factor of safety because of the issues with ongoing corrosion, and this is one of the things that we run into all the time. And even though you increase the inhibitors, increase the biocides, increase the cleaning frequencies, the problem is if you have scale buildup, it's impossible to get down to once mix starts in these areas. So keep that in mind. So doing more mitigation may not help in cases like this. These procedures, I'm jumping around here. you know, we need to think about the exceptions, the limitations of the girth weld, the long seams, related heat affected zones. This wasn't doing it before. I don't know why it's doing it now. Gouges and grooves, defects introduced during the pipe and plate manufacture, such as seams, laps, rolled ends, scabs, and slivers. I don't know if anybody's ever been in the pipe mill, but I highly recommend, if you haven't, to see what goes on in the pipe and plate manufacture. It's a it's really something to see, and how they address some of these problems when they end up with the pipe coming out, and how they grind them out, and so on and so forth. It's a challenge, I got to say that. However, by removing many of these defects by buffing and grinding, these defects can be assessed as metal loss. Hopefully they didn't make it to the field. That's the whole thing. But if they are, again, we need to consider stress concentrators with anything like that. And they need to be removed and also tested to make sure there's no other cracking involved. We got the BGs for the multi-screening process, RString for the effective area. The calculated failure pressure is then multiplied by the appropriate safety factor. And then the decision is made to repair or not to repair. Again, here's another point along the process where the probabilistic risk program could help in this decision making. The other thing is this is what the new RString program looks like. As you could see, the MALP is 921. It failed. Why? Because of long length corrosion. And this program will calculate these areas, all 3 areas. This would be number 1, number 2, and number 3. This is me making it going back and forth. And so you could see from 94 to 103, 10 to 19, and 60 to 67. And here it is. And this program will do this automatically for you. It'll give you the table. It'll tell you there are 3 effective areas that need to be repaired. And you could put a type B sleeve, for this long length corrosion. A lot of times when you get that length, it's difficult to put a sleeve on. But maybe you could put maybe 2 or 3 sleeves on and get the same effect, such as this. And you notice the factor of safety is the lowest, and it increases. And once it gets up above for a 0.72 design, it would be 1.3, 1.38, 888, or 1.39, and then the rest is okay. So these are the areas that would be repaired with a sleeve. We call it the zero out method. And if you repaired those, this is what you would get in your calculations. And you notice the BG still failed. Interesting. Why? Because their factor of safety is below 1.39. So this is something you could use. It's a time saver and a money saver. The other thing is one of the things the regulators keep harping on is digitization and mapping. So once you have your data digitized, all of this, once it's digitized, you could easily map it to where it's located and things of this nature, and you're meeting the mega rule requirements of being traceable, verifiable, and complete. So this is why it's that important. I'm gonna go to the end here. And then why is RString as the solution? Because we're talking about verification, validating, and optimizing the inline inspection, of course, with the assistance of the the probabilistic risk program. You could use to be part of critical engineering assessment. You're going to still need that. No one system is perfect. You could use repair methods such as the zero out method that I talked about right here, where it identifies all the areas, all the effective areas. Just want to point that out. And then and then we could use to determine the remaining life. And I didn't mention these over here: time to failure, remaining life, reassessment intervals, and of course the C-FER calculation. I remember when that came out. I was on the team with on ECDA team for industry, and I'll never forget when they introduced that program up in Washington D.C. So so the nice thing about this is the progress that we've made, and then determine and then to meet the traceable, verifiable, and complete through data integration of all of technical toolboxes applications. In other words, what I'm talking about, an example is if you were using the crossing applications to determine the stresses over the pipe, you could easily turn on our little graph called RString. And if there's any investigative digs in that area, they'll all come up, and you could select the one that is appropriate to that location. So this is what we're moving towards, is true data integration, and also the ability, not just data integration, but to bring all your data easily through management of change. So when there is a repair, when there is mitigation done, when any of these come up, the nice thing about it, you don't have to chase it down. It could all be integrated. And this is why I bring a lot of this up. And now I think we are going to do some questions. I don't know how much time we have. We have about 2 minutes. I'm sorry we took so much time up, but Nick, do you have anything we could answer a couple questions?
Yeah, so just a reminder for everybody still on the line, there is that question and answer pane on the right-hand side. So if you did have questions that came up throughout the presentation, go ahead and put them in the question box there. As well, if we could just post, we've kind of a very quick poll today, just kind of given, we split up the content a bit. So we want to make sure you're getting the right questions and kind of the right information answered accordingly. So, if you want to kind of fill that out, should take just no more than 10 seconds. Just kind of, do you want more information from C-FER? Do you want more information from Technical Toolboxes about the RString method? Both or neither? And then, kind of we'll route those requests accordingly. So with that, let me kind of, while that is filled out, let me look at questions. We had one question, Joe. Do we have software for RBI for tanks?
We have API, 653 and so on. Yes, we do have calculations for our tank programs. Yeah, corrosion rates and remaining life and things of this nature. That's correct.
Okay, very good. And with 1 minute left, we'll do one more question. Coming in front, how do I incorporate this information with geohazard risk?
Are you talking about with the mapping and things of this nature? We have layers. We have layers that could be added in there. Yes.
Very good. Well, for the rest of the questions, I think we will go ahead and just allow kind of the standard email follow-up. So everyone will be getting the recording of the presentation here today within 48 hours. And from there, we will route your following questions accordingly. So with that, thank you, everybody. Thank you for your time and attention, and we hope you all have a great rest of your day. Bye-bye.
Thank you.
Thanks, everyone.